Let's talk about statements now. So much of what we're going to write is called a statement. So when we create variables, we're writing statements. When we change the values of those variables, we're creating statements or using statements. When we make function calls, which we'll talk about in a few later lectures, those are statements. Each of these is a statement. Each should be terminated by a semicolon. Another thing, though, to keep in mind as we write our code is that, for the most part, it's processed top-down. So declaration statements are where we're creating variables, which essentially any program I write will need to do that, or any program that does anything of any real use. And one thing to keep in mind is that if you're compiling for C89, all variables must be declared at the top of a block. And a block is a set of curly brackets. So within a function, you may have multiple sets of curly brackets. Each of those is considered a block. And at the top of each of those, you could be creating variables or writing declaration statements. So here's an example where I'm declaring two different variables. One is an int called cost, and the other is an int called age, and I give age an initial value of 42. So both of these are setting aside a spot in memory that I will refer to by its variable name. Let's see what happens, though, when I'm trying to print out some initial values. So I've included the standard IO library so I can do some printing. Here's my main void, starting curly bracket, closing curly bracket, and cost, and age equals 42. Let's print each of these. Cost is an integer, so we want to use %d here, and I'll put a new line, so whatever's printed afterwards will be on the next line. And now let's print age, which is also an int, so I'll use the %d again. Let's compile. C9, my example. Run it. And it says that cost has a value of 0 and age has a 42. The only one of these that I can know with certainty will be what we see in the output is the 42. So in a later lecture, we'll talk more about bits and bytes and how values are represented in a computer and all those types of things. But just realize that within memory, information is stored using bits. And so you can think of those as being like a bunch of numbers. And so there's always bits there. When I allocate memory to store a cost, and I say int over here, this is saying allocate a certain amount of memory and interpret those bits as an int. If I'd said double, then I'd allocate a certain amount of memory and interpret those bits as a double. But this is what that's saying. But no part of this statement here, because it's inside main, is telling it to give it an initial value of 0. That just happens to be the way it worked out. So you should not look at this and say, even if you think that cost needs to initially be 0, don't say that, well, since it was 0 this time, whenever I run my program, it's going to be good enough. Because there may be another time when you run it and the particular spot in memory that you're given to store your cost has a bit pattern that's not interpreted as 0. So don't make that assumption. But the 42 is what it should be. So this is what we just talked about. You should always assume, or at least in most cases, we'll talk about global variables much later, and they're the exception. But for locally defined variables, which is what I have here, assume that if the variable is unassigned, then its value is garbage, because I don't know what the bit patterns will be at that time. We saw in our introductory lecture that when I had an int with a value of 9 and another int variable with a value of 4, and I divided 9 divided by 4, instead of getting 2 1/4 like you would if you were doing the math by hand, we actually got 2. And we explained the reason why was because when you divide an int by an int, you get an int. So you may think, well, I need to actually get 2.25, and a double can store 2.25. So let's write double D, and then use D is equal to num divided by denominator, and print out the answer. And notice here, when I'm printing double, I use %F as the format specifier. But when I print the answer, I get 2.000000. Why is that? Well, the 6 zeros are because the default precision of printing for %F is 6 decimal places. But what's important here is that I didn't get 2.25, I got 2. So why is that? Well, let's look and see how this works, but let's look first at the C precedence table. Excuse me. So there are lots of operators, as you can see here, available in C. And so since multiple operators can be part of the same statement, we need some way of deciding which ones are operated on first, because the order in which you process the operators can often make a difference in the result. Just like in arithmetic, there's an order of operations, right? And in fact, if we look here at precedence level 3 and 4, this shows, just like for arithmetic, that multiplication and division have higher precedence than addition or subtraction. So if you have a statement that combines multiplication and addition, the multiplication will be operated on first. If we look at the bottom here, we can see at line 14 that these are the assignment statements. There's lots of different versions, and we'll talk more about some of these momentarily. But here's our single equal sign that we use for an assignment. So if we look and see what I've written, we can see that I have a double variable equals an int variable divided by an int variable. And so the division has higher precedence than the assignment statement. So what that means is the int divided by int part is operated on first, and it produces an int, which in this case is 2. And now that 2 as an integer is assigned to our double. So it gets converted into what we'd call the floating point representation of 2. That is something that could have a decimal part if we needed to. But the problem is, when I write int divided by int, my 2.25 loses the 0.25. And there's no way of getting it back, so it's too late. So what can we do about it? Well, there's several things we can do, but one of those is to cast one of these variables to type double first. So what that means is I'm going to write this. I'm going to say in my code, D is equal, in parentheses, double, since that's the type I want. And then I'm going to have my numerator variable, it's called num, and then slash to num, semicolon. So what that means is, for the sake of this calculation only, for this use of the variable num, this will temporarily be converted to type double. And whenever I have double divided by int, then the result will be a double. And likewise, if I'd had int divided by double, I'd get a double, and double divided by double also produce a double. So let's see if it really works out that way, like I said. So we use this existing code. Double D, no initial value because it doesn't need it. Int num equals 9, comma, num equals 4, semicolon. We'll print the result here, but first we need to calculate the result, of course, so I don't need a space. I could have the space, that's just a preference not to have a space in there, but I could have. D is equal to num divided by num, just to confirm that it's going to give us 2 and not 2 1/4. And the format specifier we need is %F, because we're using floating point numbers. Because D itself is a floating point number. It's just that our 2 gets converted to a floating point number instead of 2.25. Put a new line in there. Let's see what happens. In fact, I can do all this at once. Let's now come down here and say double right there. So let's actually put 2 new lines in here to separate them. compile my code, run my code. I get 2 the first time, 2 1/4 the second time, because I temporarily cast num to type double. And just to show you it's temporary, let's do this part again. So now we're doing just int divide by int again. Oops, I didn't say that. Sorry. Let me say that. Oh, sorry, I did. I just didn't have a new line in there. So we went from 2 to 2 1/4 back to 2. Right? So this is a way of temporarily changing num into a double for the sake of this calculation. So why not just make num a double to begin with? Well, there's times when that might be the appropriate thing to do, but then there's other times when it's appropriate that num and den both be ints. We may have some reason that they need to be ints, and therefore I'm just going to temporarily convert this for the sake of this calculation to what I need. All right, let's see where we're at. So let's add some additional assignment operators. We saw these on the precedence table down at the bottom: plus equal, minus equal, star equal, slash equal, some others, right? What do they mean? There's lots of times in which I need to take an existing variable and add or subtract or multiply or divide with that particular variable in order to change the value of that variable to something else. For example, I might say double a value. Now I could create another variable. I could have said, well, b is equal to a plus 5 if I need to add 5 to a. But now I'm changing to a different variable. So I might just want to say add 5 to the existing value of a and make that the new value of a. So this is not like a mathematical equation. This is an assignment statement. And since addition has higher precedence than an assignment, this says take the old value of a, say for example if it's 10, add 5 to it to get 15, and now take that 15 and assign it back to a. But because these types of operations are done so often, someone decided just to create the shortcut version here that's a plus equal 5 in this case, or a minus equal 5 if you're subtracting 5, or so forth. So those get used probably more often than this. Now if you had to write a equals b plus 5, well then you still need to write a equals b plus 5. Another thing to keep in mind about the language is the C language is actually relatively small in terms of built-in keywords. Let's look at these. So here's a list of the 32 keywords that exist in C. And so we've seen double, we've seen int, we've seen void. We'll see many more of these as the semester progresses or as this course progresses. But there aren't that many of those. And if you look closely, you'll see there's nothing here for calculating the cosine of an angle. There's nothing here for printing. There's nothing here for getting the system time. None of those are part of the core language. So in order to do those things, people have written libraries with functions that perform those operations. And so many of those things, in fact, all the things I just described, exist in what's called the standard C library. And so that's the reason why at the top of our code, when I need to print, I have to say pound includes standard IO, because that's the library that contains information about printf. Without this line right here, I'd get a compilation error because the computer would know what int meant, it would know what void meant. Of course, it knows what main, well, actually, it doesn't have to know what main means. But, or it does in the sense of knowing where to start, but it's not a keyword. It knows this int, but it would not know what printf meant, so it would give us an error message. And so that's the reason why I include this. And if I wanted to find the cosine of an angle, I'd include the math library, and so forth. Because we're going to use printf so often, we need to talk more about how to alter the way it works in terms of the format specifiers. So when I'm printing ints, the format specifier %d is the way of saying take this int, because a was defined to be an int, or declared to be an int, take this int a and put its value right here. Over here I just say a, so it doesn't put in 23, it just writes a. But I want the value of a right here, so that's why there's the %d. And so wherever I put the %d, that's where the number starts. So notice that a has a value of 23, which takes up 2 digits, B is 1,000, which is 4 digits. So each of those just starts printing at the place where I wrote the %D. But as a person who's used to reading English numbers, I'm used to the convention that numbers are aligned with the decimal place, or if there are no explicit decimal places, we think of everything being right justified. And so by writing things that way, the magnitude of the numbers increases to the left. So the numbers that stick out farther to the left are the ones with the largest magnitude. And so I'm used to that. So how do I achieve that here? Well, I can put a number in here to give me a minimum number of spacing, and then pad on the left if necessary, if the values I'm printing take up less than in this case 5 characters of spacing. So 23 only uses 2 characters of spacing. So here I have A space is space, and then I'm going to have 5 characters of spacing for 23. And so since the 2 digits of 23 are less than 5, I'm going to get 3 characters of spacing on the left. 1,000 is 4 characters, so I get 1 space on the left in this case. There's some other options. I can mix things within the same line. So the %4D affects just the A, while %D is used for the B here. Sometimes I want to pad with zeros instead on the left. So if I say %04D, I get 4 characters of spacing, with the 2 zeros representing the 2 additional spaces I need in addition to the 23. And then if I want the spacing to be left justified with spaces added to the right if necessary, I can use the minus sign like I do here. So the -4D, when I'm printing 23, says print 23, space for that. Then there's a space that's automatically before I print 1,000, and then I see 1,000. What about floating point numbers, which are things of type dub or type float? Well, if I just say %F, then I automatically get 6 decimal places of precision shown. But sometimes I want to change that. So in this case, when I write 6.4F, this says give me a minimum of 6 characters of spacing, counting the decimal point that you see down here, with 4 decimal places of value to the right of the decimal place, and then round off what you show if necessary. It doesn't change what's stored, it changes what you see. So since 8 would typically force the 7 to the left to round up, that's why we get 0.4568. But this overall number actually takes 8 characters of spacing, so it just fills up the whole spot. Notice that when I say 10.4F, I get 2 spaces here to the left, because you have space, that's 2 characters, 3rd character, 4th, 5th, 6th, 7th, 8th, 9th, 10. The 8 here is the 10th character, and so the extra spacing's on the left. What about getting information from the user? Well, for that we can use Scanf, because lots of times I want to ask the user for some information instead of hard coding it into my program and then use it. So we'll explain this. Let's write that code or something similar to it and explain what we're looking at. In fact, let me get out of this actually, because I had something extra there. In fact, why do we need printf? Let's do this. Let's see what happens if I don't use the printf statement here. Notice it doesn't tell me what it wants. Scanf is simply just sitting there waiting on me to type something in. So as the user, I don't know what it's expecting. So that's why the printf would be. So in this case, it wants an age. I'm going to type that in, and it uses it. But you almost always, for these types of programs, need to include a print statement that tells the user what you expect. So by not including a new line here, then the cursor will be on the same line. So now let's compile and run it again. So this looks fine. Now at least I know that it's waiting on me to type something in. I type in the value and I get this right here. So how does this code work? Well, I still need a format specifier for scanf for the type of variable that it's reading in this case an int. For the most part, the format specifiers match what they would be using, or what they would be if I was using them in printf. Like in this case, if I was printing an int, I'd use %d. If I'm using scanf for an int, I'll also use %d. Why is the ampersand here? We'll talk more about that later, but the short answer is it's getting the address in memory for this variable, because scanf needs to know where to put the answer. And then the rest of it's just like what we've seen before. So I've already stated a lot of this, and that is basically that if you don't tell the user what you want them to enter, then they may not even know that you're waiting on them. You have to use a format specifier for each variable that you're reading in. For the most part, they're the same as they are for printing, with one notable exception, and that is when we talk about numbers that can represent decimal parts, we're going to eventually talk about two types. One of them is called a float, and one is called a double. If I was printing a float or a double, I can use %f for either one. That's fine. But when I'm using scanf to read in a float, I need to use %f. But if I use scanf to read in a double, I use %lf, where this is a lowercase letter l. And then we saw that I have to also use an ampersand when I'm reading in, at least for numeric types. So we'll pick up on something else in the next lecture.